So hello to everybody, welcome to ITMP seminar. So today, Mitya Ponomaryov, who usually chairs the seminar, is busy. He's on the conference, so he asked me to take care of it. And we are happy to have Kurt Hinterbichler. I hope I pronounce correctly, more or less.
Yeah,
Who will
very
tell
good.
us about shift symmetries, equivalence of EFTs, and timelike extra dimensions. So please go ahead. You have something like 1 hour.
Okay,
And then we have questions.
great. Thank you. So yeah, thank you very much for the invitation to speak at this. So I was asked to talk about this paper here, this recent paper with Samantha Saha, who's my student at Case Western. And Samantha's here in the audience. Hi, Samantha. So this is a project we did, which I think gives some interesting lessons about effective field theory, especially when you have geometric type constructions. So let me start with the standard picture of a spontaneously broken internal symmetry. So here's a picture of a standard symmetry breaking potential where you have some scalar field here that parameterizes your different vacua. And when you have a situation like this where you pick a certain vacua, there's always some direction, which is going to be a flat direction, which appears to the Goldstone boson like a shift symmetry to lowest order in the field. So when you have spontaneously broken symmetries, a hallmark of that is a shift symmetry. So when you're expanding in powers of the field around some broken vacuum like this, at leading order, you always have a shift symmetry, some shift by a constant, and then at higher orders, there can be various field-dependent parts. And as long as this constant part is non-zero, then you have a broken symmetry because it doesn't preserve the vacuum where phi equals 0. Whereas if you don't have that constant part, if you just have field-dependent parts, then the symmetry is unbroken because it preserves the vacuum. And if you're looking at a Lagrangian now in powers of this field, the fact that you have this leading part, which is a shift symmetry, it tells you that the leading part of the Lagrangian has to be a standard kinetic term without a mass. And that's the standard massless Goldstone boson that you have when you have a spontaneously broken symmetry. So now if we want to write interactions, if we assume to start for simplicity that the shift symmetry is all there is, that there's no higher order stuff in the field, and we ask for what are the invariant interactions that you can write down. So anything that you write down that involves at least a derivative of the field is automatically going to be invariant. So you can call these, if you like, this d mu of phi, the derivative of the field, is like an invariant building block, and any function of this and its further derivatives is automatically going to be invariant. There's one other possible term you can write, which is in some ways more interesting because it's not made out of this invariant building block. In this case, it's just constant phi. This is also shift invariant. This is what's known as a Wess-Zumino term, that it can't be built out of this invariant building block. Okay, so we're going to be interested in how does this extend now to shift symmetries that also involve the space-time coordinates, that don't involve just the standard internal symmetries that we're used to. So the basic question is, can shift symmetries involve the space-time symmetries in a non-trivial way? And the first thought you should have is that there's this Coleman-Mandula theorem that says that if you have symmetries of an S matrix, it can only be of the form, the Poincare symmetries, the space-time symmetries, direct product with the internal symmetries. So there can't be anything interesting that any non-trivial commutators between internal symmetries and the Poincare symmetries. However, this doesn't actually tell you anything directly about broken symmetries, because broken symmetries are not directly linearly realized on the S matrix. Instead, they're realized usually as soft theorems, or zeros. As you take certain momenta of the S matrix to zeros, you get identities between higher point scattering processes and lower point scattering processes. So they don't fall under this theorem. So we'd like to know, can we classify the possibilities for what these broken space-time symmetries can be? Okay, so as a starting point, we'll to make things simpler, we'll stick to just a single scalar field. And if you look at the kinetic term for a single scalar field, you notice that it's also invariant under shifts like this, where you have a constant times the spacetime coordinate, x mu. So this is, people call this a Galilean symmetry because it's kind of like the space-time version of a constant boost. And the kinetic term is invariant under this. Also, if you write down any interactions that involve now two derivatives of the field, so anything involving this building block with two derivatives of the field is automatically going to be invariant under this Galilean shift. So these are, if you like, the boring interactions that you can just write down any function of this building block, and you're going to get an interaction that has this symmetry. But there's also a finite number of interactions which are more interesting, that are not just made out of this building block, that involve fewer than two derivatives of the field. And that's these so-called Galilean terms, which are Wess-Zumino terms. They're analogous to this tadpole term that we had for just the simple shift symmetry. So it turns out that there's 5 of them in 4 dimensions. In d dimensions, there'd be d plus 1 of them. And they look like this, and you can classify them. We can also ask, is it possible to deform the symmetry? So is it possible to add higher order pieces to the transformation law that now involve powers of the field that still close and give you a symmetry? And for this simple Galilean shift, the answer is yes. And there's 2 sort of independent ways to do this. The first way looks like this, and it gives you a Lagrangian, which is the square root, famous dBi square root Lagrangian, which we're going to talk much more about. And you find that the algebra of symmetries now becomes non-abelian. It becomes the isometry group of a higher dimensional space with a signature that's going to depend on the sign of this lambda, which we'll talk much more about later. And then there's another possible deformation that looks like this. And this gives you what's known as the ADS dBi theory, which is described by a brane probing a higher dimensional ADS space, which we'll also talk much more about. And this gives you an algebra SO2, 4, regardless of the sign of this. And we're going to talk much more about that later as well. So these are going to be our main examples going forward. But first, let's see what else there can be to higher order. So now if we look back at the kinetic term again, we can do a shift by something which has 2 powers of the spacetime coordinate contracted with some symmetric traceless constant tensor. So this is also a symmetry of the free Lagrangian. And again, you can write down any sort of boring interaction that involves 3 powers of three derivatives acting on the field. But there's also, in this case, a more interesting set of interactions, which is non-abelian, which deforms the symmetry in a non-trivial way. It looks like this. And this is known as the special Galilean. And there's a single unique Wess-Zumino-like term that you can add that's invariant. And this gives you some non-abelian algebra, which is some contraction of SL6 when you work it out. And you can go to higher powers of x now. So the free Lagrangian has symmetries where you have arbitrary powers of x times some symmetric traceless constant tensor. But if you go beyond 2 powers of x, if you ask for some non-trivial algebra that these symmetries could satisfy, so they always have these trivial interactions where you just have powers of derivatives, but if you ask for these more interesting interactions that deform the algebra, you find that there's nothing you can write with 3 or more powers of x. So there don't seem to be any of these more interesting non-trivial effective field theories at higher orders. So there's various ways to see this. One is just by trying to write down the algebras that you could possibly have and showing that they don't exist beyond higher order. That's in this paper here. Another way to see this is directly from the S matrix. So you can classify what kind of soft behavior can there be for an S matrix of a single scalar, which you'd expect there to be if there were these kinds of shift symmetries. So on this plot here, this row on the y-axis is basically the number of derivatives per field in your Lagrangian. And this sigma here is soft behavior. So as you take one of the legs of an amplitude to zero, one of the momenta to zero, the amplitude vanishes with some power of the momenta sigma, and that's what's being parameterized here on the x-axis. So if you have a certain number of derivatives per field, you're automatically going to get a certain type of soft scaling behavior. That's what this blue region is here, trivial soft behavior, just from having enough derivatives. But there are a few theories which go beyond this blue region. So that's the special Galilean, this dBi, which was the non-trivial deformation of the ordinary Galilean. And then here's nonlinear sigma model, which is if you have multi-fields, this the non-trivial deformation of the ordinary shift symmetry. So these theories here have a better soft scaling than you'd expect from the number of derivatives in the field. So this is the S-matrix way of saying that these are this non-trivial interactions that deform the algebra. And then beyond those few examples, there's nothing else allowed for a single scalar. Okay, so we're going to be interested in this deformation of the Galilean symmetry, so the symmetry involving a single power of x. So let's first look at this dBi theory. So that's this deformation here. So if we look at the full symmetry group, so there's the unbroken symmetries, which are their usual Poincare transformations, the Lorentz transformations and the translations. And then the broken symmetries are the shift symmetries. There's the ordinary shift symmetry that's there just because you always have a derivative on phi. And then there's this extended shift symmetry that was the deformation of this Galilean symmetry. So now you can group together the Lorentz transformations J and these extended shifts into a 5-dimensional antisymmetric matrix, and you can group together the 4 translations and the shift C into a 5-dimensional vector, and then you find that these form the algebra of a 5-dimensional Poincare group. So that's being broken down to the 4-dimensional Poincare group because these are non-linearly realized. These are linearly realized. So the symmetry breaking pattern is from 5-dimensional Poincare down to 4-dimensional Poincare. The isometries of a space with signature 1, 4 being broken down to a space isometries of a space with signature 1, 3. So we realize this geometrically. We can construct this theory as the theory of a brane, a free brane that's fluctuating in a higher dimensional space that's a fixed 5-dimensional Minkowski space. So we have this ambient metric, which is a fixed 5-dimensional Minkowski space. So there's one extra dimension transverse to the brane. And here's the 3 branes, so 4 world volume dimensions. And this x capital A is parametrizing the fluctuations of the brane into the higher dimensions. So little x is the coordinates on the brane, big X is the coordinates in the ambient space. And we want to write down actions which are going to be invariant under these higher dimensional Poincare transformations. So that's this global symmetry here. Omega is the boosts in the higher dimensions, epsilon is the translations in the higher dimensions. And then we also want it to be invariant under reparameterizations of the world sheet of the brane. So that's what these are here. These x's are scalars from the point of view of the world sheet of the brane. Xi mu is some arbitrary infinitesimal diffeomorphism on the brane. So now what we typically do is we fix a kind of unitary gauge where we fix the coordinates on the brane to be the first 4 coordinates in the bulk, and then we let the 5th coordinate be the fluctuation of the brane into the bulk. So phi is like the brane bending mode into the bulk. And when we fix this unitary gauge, when we do a Poincare transformation, we generally have to do a compensating gauge transformation to get back into this gauge. And the combination of the two then gives you exactly the symmetries that we wrote down before. The extended shift symmetries correspond to the Lorentz boosts away into the 5th dimension, and the ordinary shift symmetry corresponds to the translation into the 5th dimension. And then you have the unbroken 4D Poincare transformations left. Okay, so when we want to write down an action, what we want to do is write down something that's made out of diffeomorphism invariants of the various geometric quantities on the brane. And then we use this, we put them in this unitary gauge, and then we're guaranteed to have an action that's invariant under this symmetry. So the various ingredients we're allowed to use are the induced metric on the brane, which looks like this in the unitary gauge. There's the extrinsic curvature on the brane. Then there's the covariant derivative and the curvature made out of the covariant derivative of the brane. There's also a Gauss-Codazzi equation on the brane, which relates the extrinsic curvature to the intrinsic curvature, plus some bulk curvature things which are constant. So we don't need the intrinsic curvature on the brane because we can always exchange it for extrinsic curvatures. So the most general Lagrangian one can write down is some arbitrary function of the metric on the brane, the extrinsic curvature, and various powers of the derivative. So now there's a derivative expansion. Each extrinsic curvature comes with a derivative. The covariant derivative is a derivative. So you can write this f as a derivative expansion which starts with nothing, and then the extrinsic curvature, and then the 2 derivative terms, 3 derivative terms, and so on, keeping in mind that you can always integrate by parts and so on. So the lowest order piece is just this constant here, which is just the volume on the brane, the 4 volume, which gives you this square root dBi action when you plug in terms of the scalar field or the brane bending mode. There's one term which is missed by this, which is the so-called Wess-Zumino term. And you can construct this by considering the 5 volume that the brane parameterizes from some arbitrary fixed reference point in the bulk. And this 5 volume is just proportional to phi itself as a Lagrangian. So this is a 0 derivative term. This is a tadpole term. And we won't need it because we'll generally have to set this to 0 to have a solution where you have phi equals 0 being a solution. But we will need this when we go to the ADS case. So this is the one term that you can't construct from just these geometric invariants. So another thing that's going to be useful is that at each order in the powers of these geometric quantities, there's a unique term that when you write it in terms of the scalars, it gives you second order equations of motion in terms of the scalars. In other words, it doesn't propagate any extra degrees of freedom, even non-linearly. So this is going to be very useful when we're talking about field redefinitions, just to restrict to these terms because they don't give you extra degrees of freedom. So at each order in the curvature, there's a term we can write down, the Lovelock invariant. So the leading one is just a constant. The next one is the Einstein-Hilbert one. The next one after that is the Gauss-Bonnet, and so on. These are just the things where if you integrate them over a 2m dimensional manifold, you'll get the Euler number of that manifold. So they're total derivatives in this dimension 2m or any dimension lower. And each one of these also comes with a boundary term. So there's a Gibbons-Hawking-like boundary term for the Einstein-Hilbert action. There's a boundary term for the Gauss-Bonnet term, and so on. So if we use these, we're guaranteed to get second-order equations of motion. So if we're talking about 4 dimensions, 4-dimensional brane, these are the terms we have. We have a cosmological constant on the brane, which we already saw as the lowest order term. There's extrinsic curvature, a trace of extrinsic curvature, which we can think of as the boundary term for a bulk Einstein-Hilbert term. There's then the Einstein-Hilbert term on the brane. Then there's this boundary term for the Gauss-Bonnet bulk invariant. And then beyond that, everything's trivial. So there's only 4 of these in 4 dimensions. When you use Gauss-Codazzi to express these all in terms of extrinsic curvatures, they turn into symmetric polynomials. So these are just the polynomials if I have some matrix M, the anti-symmetrized combinations. These are the things that appear when you expand the determinant of the matrix. So you just get these special Lovelock terms are just symmetric polynomials in terms of the extrinsic curvature. And when you write them out in terms of the field, they give you what people call the dBi Galileans. They're terms which are kind of non-abelian extensions of the Galileans, but still preserve this property of having second-order equations of motion. So there's 4 of them in 4 dimensions, plus the one tadpole term that we've ignored here. Okay, so let's look at this lowest order dBi term. And let's consider the S matrix, which is useful because it's a quantity which is observable. It's independent of field redefinitions. We can tell exactly when things are different by looking at their S matrices and asking whether they're different. So if we expand this around a constant solution, we get the kinetic term. The leading interaction we get is this d phi to the fourth interaction. Lambda here is just a length scale that we've put in to give the fields its canonical dimensions. So if we look at just the tree level 4-point amplitude for scattering of phis, we get this this contribution, in terms of the Mandelstams, s squared plus t squared plus u squared. And this is consistent with these famous positivity bounds of these guys here, which have been extremely generalized in recent years. But basically, they said that this coefficient here has to be positive in order for this theory to have a normal field theoretic Lorentz invariant UV completion. And that comes out because of the positive sign here. And this is the only contribution you have at order s squared to the S matrix. If you include any of those higher order Galileans or anything else, you would get higher order contributions here. Okay, so let's go back to this geometric construction. So what happens if we have an extra dimension now that has a timelike extra dimension? So the fifth dimension now, we're going to put another minus sign in the metric. So the bulk spacetime is now a spacetime with two time dimensions. When we do this, the induced metric now gets an extra minus sign. The dBi term gets another minus sign here. If we compute the amplitude, there's now a minus sign in front of the d phi to the fourth term. And so you get an amplitude with a minus sign here, which violates the positivity bounds. So this is now a theory which is known as the wrong sign dBi theory. And if you look at the shift symmetries now, there's a minus sign here in the transformation. And if you work out what the algebra is, it's now the algebra of the isometries of a higher dimensional space with two time directions. So it's a group isometries of a space-time of signature 2, 3, which is a different group than the group with the plus sign where we had 1, 4. So it's a different symmetry group, different symmetry breaking pattern. And so, of course, we get a different theory, as we expect. This theory is not equivalent to the correct sign dBi theory because the amplitude comes with a different sign, and the amplitudes are completely if you have two different amplitudes, you know the theory is different. There's no field redefinition or anything that can connect you between the two. So these are two independent, different deformations that you can have of the Galilean term, depending on this sign here. Okay, so this conforms with our intuition about effective field theories and how they are determined by the symmetry breaking pattern. So the typical Landau-Wilson paradigm that we have for low energy physics is that everything is supposed to be determined by the symmetry breaking pattern and the types of degrees of freedom, the light degrees of freedom that appear at low energies. So if you know what the light degrees of freedom are, and if you know that what the symmetry breaking pattern is that they realize, that's supposed to explicitly determine the low energy dynamics of the theory. So that should go as well for effective field theories, because effective field theories are supposed to capture all of the low energy dynamics. So low energy effective field theories should be completely determined by what their symmetry breaking pattern is and their light degrees of freedom. And the question is this true also when you have space-time symmetries? So the example we just saw, it seems to be true. We have these two theories with different symmetry breaking patterns, and we got different answers for the physical observables. Okay, so here, let's go now to this other example, this other deformation, where we have this this different deformation of the Galilean symmetries. So this, if we look at the algebra of transformations here, we get this, which is nothing but the conformal group. So the generators, the shift now we're calling D, the Galilean-like transformation we're calling K to conform with the notation that people use in conformal field theory. And if you take these and group them up into a six-dimensional matrix that looks like this, then you see that these satisfy the commutators of an SO group with a metric that looks like this, with two two times in it. So the symmetry breaking pattern is SO2, 4 down to SO3, which is just the conformal group being broken down to the isometries of ordinary Minkowski space. Okay, so we can realize this geometrically by considering a brane probing a higher dimensional ADS space. So if I write down ADS metric in the Poincare patch, it looks like this, where rho is the radial direction, L is the radius of the ADS space. And now we do the same geometric construction. Here's what the induced metric now looks like. You get these extra warp factors from the ADS. And now for the dBi term, the 0th order, the lowest order geometric invariant, you get this, which has these extra exponential warp factors in it. So now if we look at the S matrix, so we expand this out, and here we've had to add the tadpole term to ensure that we have a solution where phi equals 0. So we get, again, the kinetic term. We get some cubic terms, but these are all trivial on shell. They don't contribute to the 4-point amplitude, or rather you can redefine them away. And then you get this d phi to the 4th interaction again with a plus sign. So the amplitude looks the same with this plus sign, consistent with the positivity bounds. Okay, so anti-de Sitter space, it's well known from Dirac that you can realize this as an embedding, as a hyperbola embedded into a higher dimensional Minkowski space with two time directions. So the ADS hyperbola, we'll call this ADS 1, 4 to remind the signature of the ADS space. We can embed this as a hyperboloid in a Minkowski space with signature 2, 4, like this. So Y here is now the embedding of this ADS hyperboloid into this higher dimensional two-time Minkowski space. And the advantage of this is that it manifests all of the isometries of the anti-de Sitter space. So the boosts in this higher dimensional space are the isometries of the anti-de Sitter space, and the group of boost transformations here is just SO24, which is the group of transformations of the anti-de Sitter space. So then we can write down the Poincare coordinates and get this induced metric, and these coordinates manifest the subgroup of isometries of 1, 3, and then the others all become hidden in this particular coordinate. There's another space, though, that we can realize in this exact same embedding space if we instead take the hyperboloid where we put a plus sign here. Then we get another space with the exact same isometries as anti-de Sitter space, but now it has positive curvature. So this is a spacetime that we'll call two-time de Sitter space. So it's a de Sitter space, a maximally symmetric space of constant positive curvature, which has a signature 2, 3. So it's a de Sitter space with two time directions. So it lives in the same embedding space as anti-de Sitter space. So it has exactly the same isometry group, SO2, 4. And we can write Poincare coordinates for it. And the induced metric now looks like just the ADS metric, except there's this extra minus sign here going in the radial direction. So this Poincare-like coordinate also manifests the same unbroken isometry group of ordinary Minkowski space. Okay, so we can consider now a dBi theory where we have the bulk brane being this de Sitter space with two time directions. So we have a flat brane probing this two-time de Sitter, so the extra dimension is now timelike. So the induced metric now has this extra minus sign here, and the symmetry transformations now look different. There's this extra minus sign, but the group, if you compute all the commutators and ask what group this is, we know that it's exactly the same because the isometry group is exactly the same as it was for anti-de Sitter. So the symmetry breaking pattern in this theory is exactly the same as it was in the ADS theory, even though the transformation looks different. If we look at the dBi Lagrangian, there's now some extra minus signs in the square root, and when we expand, this d phi to the 4th interaction now has an extra minus sign, and so the 4-point amplitude now has this extra minus sign, which violates the positivity bound. Okay, so now it looks like we have an example where we seem to have two different effective field theories where they have exactly the same symmetry group and the same symmetry breaking pattern. They both have this SO2,4 symmetry being broken down to four-dimensional Poincare group. And yet the amplitudes are different. So it seems to be two completely different theories with the same symmetry breaking pattern. So is this a counterexample to our expectation that the symmetries plus the degrees of freedom fix the low energy dynamics of the theory? Okay, so our goal is going to be to resolve this apparent counterexample. So let's go look a little more closely at this intuition of why we expect the symmetry breaking pattern and the degrees of freedom to fix the effective field theory. So if we go back for a second to the case of internal symmetries, so symmetries that commute with all the space-time symmetries, there's a construction known as the coset construction, which kind of manifests this statement that the theory is completely determined by the symmetry breaking pattern and the degrees of freedom. So the coset construction allows you to construct an invariant Lagrangian if you are given a symmetry breaking pattern and a set of degrees of freedom. So the symmetry breaking pattern, if you should be given a full symmetry group, the unbroken subgroup, and then you know that by Goldstone's theorem, the Goldstone's bosons should live in the coset space of the full symmetry group modulo the unbroken group. So what this construction tells you how to do is make a Lagrangian that describes the dynamics of these Goldstones. So what you do is you start with a basis of your full symmetry group where you have the unbroken symmetry generators that we call Z, parameterized by I, and then you have the broken generators that we call Z, parameterized by little a. And then you write down this coset element, which is the exponentiation of these broken generators times these fields Xi, and these Xi's are going to be the Goldstone bosons. There's one of them for each broken generator. So you construct this Maurer-Cartan form, this differential, you expand it back over the generators, and the coefficients that appear here are now ingredients that you can use in the construction of the Lagrangian. So the coefficient that appears here in front of the broken generators, these involve the Goldstone bosons, so this is like an invariant building block that you can use to make the dynamics of the Goldstone bosons. And the part that appears here transforms like a connection. It's something that you can use to make a covariant derivative, to take higher derivatives of this, or to couple in matter, or other degrees of freedom. So your invariant Lagrangian now can be any function of these invariant building blocks, which you then expand as a power series in derivatives, and that gives you the effective field theory expansion. And then there's always, or usually, some finite number of these Wess-Zumino terms that can't be constructed from these invariant ingredients, and these are classified in a different way by Lie algebra cohomology. Okay, so this, in the case of internal symmetries, this kind of manifests this expectation, or if you're given a symmetry breaking pattern and a set of degrees of freedom, you just get from this procedure an invariant Lagrangian. There's no wiggle room. But now in the case of space-time symmetries, it's a little bit more subtle. So in the case of space-time symmetries, we again have some full symmetry group, some unbroken subgroup. But now the full symmetry group and the unbroken subgroup can involve some of the space-time symmetries. So when we construct the coset element, what we're supposed to do is include the unbroken translations among the broken generators, just because formally, if I have some coordinate, the way it transforms under translations is to shift the coordinate. So even though it's unbroken, it formally looks like a broken symmetry, so we have to include it in this coset. And then when we expand, we again get these invariant ingredients, invariant building blocks that we can use for the Goldstones and for the various invariant covariant derivatives and so on. But now, when you have space-time symmetry breaking, it's no longer true that the number of Goldstone bosons has to equal the number of broken generators. The number of Goldstones is in general less than the number of broken generators. And the way that appears is through the appearance of the so-called inverse Higgs constraints. So these are are constraints that you can impose that are invariant, and they come from looking at certain components of these commutators. If you have a commutator of a translation with some broken generator that gives you back a broken generator, you can show that setting one of these components of these Maurer-Cartan forms to 0 is an invariant constraint that you can impose at the level of the action to eliminate some of these goldstones. So this is a freedom that you have here. The theory is not completely determined by just the breaking pattern and degrees of freedom. There's this freedom to impose these constraints. Okay, so let's, for example, try to do this for the broken conformal group. So if we start with our conformal algebra, just these commutators, and try to reconstruct the ADS theory that we had. So we have our unbroken symmetries are just going to be the ordinary Poincare transformations. The broken symmetries are going to be these dilation and special conformal transformations that in our case corresponded to the shifts and these Galilean symmetries. We construct this Maurer-Cartan form. So among the broken generators, we have these Ks and Ds. So the D comes with pi. Pi is ultimately going to be our Goldstone field. Xi comes with K. Xi is ultimately going to be a redundant field that we're going to eliminate with these inverse Higgs constraints. And then the space-time coordinate here I've called Y. So we compute this Maurer-Cartan form. You can get it in closed form. The components look like this. You can look at how the coset transform and get the symmetry transformations, and it looks like this. But now we can do this inverse Higgs constraint. So there's a commutator of D with P gives back a broken generator. So you're allowed to eliminate this component by solving for this Xi here in terms of the other fields like this and plugging back. So that eliminates the Goldstone associated with the special conformal transformations and makes everything just in terms of the Goldstone with respect to the dilation. So you end up with this. So this gives you now the various invariant building blocks that you can construct theory with. So this component here gives you an invariant Vierbein, which you can make into an invariant metric that you can use to raise and lower indices and integrate. This part here gives you an invariant building block for the Goldstone that looks like this. And this actually turns out to be writable in terms of the Ricci curvature of this metric. So people usually write it like this rather than like this. It's just a trace reversed version. And then this would give you some covariant derivative that you could use to couple matter, but we'll just consider the Goldstone boson for now. So you write a Lagrangian that uses arbitrary powers of these ingredients. So in a derivative expansion, you'd start with just the root g of this metric, and then the next term would involve curvatures and so on. Okay, so again, there's going to be at each order a special term which has only second order equations of motion. That's these Galilean terms. So this parameterization that we get out of the coset construction like this is called the Weil theory. So at lowest order, you have just the root g. That gives you a term like this with no derivatives. That's like a tadpole. At next order, curvature here gives you something with two derivatives. This is now the kinetic term. So here you can see that these curvatures do not correspond to the geometric curvatures that we had before with the ADS construction, because in that case the kinetic term came from the root g, but here the kinetic term is coming from the r. At third order, you get higher order powers of the fields. And then there's this one term, this Wess-Zumino term, which cannot be constructed using these invariant ingredients, which you have to construct using other methods. That's this Wess-Zumino term. It looks like this. So this Weil theory is familiar as the theory of spontaneous breaking of conformal symmetry. So this appears, for example, in the proof of the A theorem. This term plays a leading role because it's this special term that carries the A coefficient when you're talking about spontaneous breaking of conformal symmetry. So this expression
Excuse
gives
me, just to clarify, I got a bit confused. So it's only, so the metric is always conformally flat. So it's a theory for the Weil factor pi, right?
That's right. Yeah.
So it's not a curved geometry, conformally. It's not conformally curved. It's conformally flat always.
Correct, yes.
Okay, thanks.
Yeah. So so this effective field theory now, you see that there's a nice derivative expansion. So these orders contain no derivatives. These always contain 2, 4, 6, 8, and so on. So this is giving us a theory which doesn't look like the geometric theory that we had before. These terms are uniform in the number of derivatives, whereas with the geometric theory, when we had those square roots, we had derivatives under the square roots. So when you expand, you get sort of all powers of derivatives. And yet the symmetry breaking pattern was the same. So it turns out that ADS theory we get by just choosing a different parameterization of the coset in this coset construction. So there is an ambiguity in the coset construction in that we're free to parameterize that coset any way we like. We can use any basis for the algebra when we write down that coset element. So if we choose this other basis here, where we use this k hat instead of k, which is this linear combination with this parameter L, which is at this point just some arbitrary parameter that we've introduced, but we're going to see is related to the L, the ADS scale L. When we use this basis for the algebra, we get some commutators that look like this. We go through the Maurer-Cartan form. We can again compute them in closed form. It's a lot messier now. There's an inverse Higgs constraint, which is a lot messier, but you can still do it exactly. You now get an invariant metric, which looks like this, which is exactly the invariant metric that we got from the geometric construction, the brane construction that we did earlier. So that geometric construction corresponds to this different parameterization of the coset. And then if we look at the invariant building block that comes from this element of the coset, it looks like exactly the extrinsic curvature of the brane that we got. So that brane construction, those ingredients come directly from this coset construction in this different parameterization. Okay, so here's what the Galilean terms look like now. They're again extrinsic, they're characteristic polynomials of this invariant building block, this extrinsic curvature, and the terms we get are what we got from the brane construction, where they're now no longer uniform in powers of the derivative because of these square roots. And the other thing is this Wess-Zumino term now appears as the tadpole term. Okay, so these two theories, because they relate just by a different parameterization of the coset, are equivalent theories. So I should be able to relate the coset between the two theories and get a field redefinition that relates the two theories. So that's what this is too. Here we write down the Maurer-Cartan form in the one parameterization, equate it to the Maurer-Cartan form in the other parameterization, and we get a field redefinition that relates the field pi that we got from this vial-like construction to the field phi that we get from this geometric brane-like construction. And the coordinates are also related by this field-dependent coordinate transformation. So y is the coordinates of the vial-like theory, x is the coordinates of this brane-like theory. So this is a transformation that's mixing the coordinates and the fields. If you were to rewrite this as just a transformation of the fields, you'd by like replugging this coordinate back in and expanding, you'd find that this is a field redefinition that involves all higher powers and all infinite numbers of derivatives of the other field. So it's a highly non-trivial field redefinition, but it's completely invertible, one-to-one and invertible, because it came from this reparameterization of the coset. So we can use this field redefinition. We can get the relation between the building blocks. You can show that the field line of the one transforms into the field line of the other in this way, and the building block of the vial theory transforms into the building block of the geometric theory in this way. And then you can relate the Galilean Lagrangians on both sides. So the Galilean Lagrangians are the ones that involve no extra degrees of freedom. And so they should transform into each other under this invertible field redefinition. And indeed they do. So of these second order Lagrangians on one side and the second order Lagrangians on the other side, there's a simple just change of basis that takes one into the other. And it also preserves the fact that there's this Wess-Zumino term. The Wess-Zumino term in one it becomes the Wess-Zumino term in the other. That's why you see sort of zeros in this matrix. And if you write out what this transformation looks like, so it preserves the phi equals 0 vacuum solution, it preserves the kinetic term, and so it preserves the S matrix between these two theories. But it's a highly non-trivial redefinition. So here's an illustration of this. So if I start with the kinetic term of the Weyl theory, so this was just the second order terms in this Weyl parameterization. So this here is just a free theory because it's just a reparameterization of a free theory. But if I write it in terms of this brane construction, it looks like these highly non-trivial Galileans with all sorts of square roots and derivatives and so on. So here on this side, it looks highly non-trivial, but we know it's just a free theory in disguise because it comes from this field redefinition of this free theory. So indeed, if we expand this out in powers of this parameter L, which from the point of view of the coset is just an arbitrary parameter, from the point of view of the bulk geometry, it's the bulk ADS curvature. But when we expand in terms of this L, the leading order part is just the free Lagrangian. The higher order stuff all comes with powers of L, but we know that all of this is trivial in this case. So this L here is a completely redundant parameter. So what this is telling us is that the derivative expansion in the ADS, or the geometric formulation, is highly obscured and non-trivial, because on this side here, it's just second order in derivatives. On this side here, you've got all sorts of square roots, infinite powers of derivatives. It's highly non-obvious that they all cancel on this side. Okay, so now that we know what's going on with this ADS theory, it's easy to get to the other version, the one with the de Sitter theory, where we had a time-like extra dimension. So all we have to do is analytically continue to negative values of L squared. So now we can parameterize this coset with a minus sign here, because this L was just a redundant parameter from the point of view of the coset, so there's nothing preventing L squared from being negative. So we do the same thing with a minus sign here. We get from the coset this invariant metric with a minus sign, invariant building blocks with some extra minus signs, and now the Lagrangian has extra minus signs. And we do the same equivalence to the Weyl theory. We get now another field redefinition that involves some extra minus signs that takes us between the de Sitter Lagrangians and the Weyl Lagrangians. Okay, so now we just compose these two maps between the anti-de Sitter and the Weyl theory and the de Sitter and the Weyl theory, and we get a map from the anti-de Sitter theory to the de Sitter theory. So the theory that's probing the ADS, the space with the timelike, the case with the spacelike extra dimension is equivalent to the theory that's probing the timelike extra dimension. And again, this map preserves the vacuum and the kinetic term, so it preserves the S matrix. Okay, so if we look at the S matrix, if we look at the amplitudes now in the de Sitter theory and the anti-de Sitter theory, so here's the anti-de Sitter theory now including all of these higher order Lagrangians. When we compute the S matrix, we see that the mistake we made before is not including all these higher order terms because the derivative expansion is hidden here. There are things in these higher order terms that are contributing at lower orders to the amplitude. So when we look at the order S squared part of the amplitude, you get contributions from these higher order Lagrangians. And so this leading part that was positive in the ADS case, it can actually get affected and even change sign by the contribution of these higher order terms. And when we do the same thing on the de Sitter side, when we include the full set of interactions, we get contributions here. And so the leading part was that minus sign that we saw before, but now there's these higher order contributions. Z here is just some kinetic normalization of the kinetic term. So now there's the map that we got from these two theories tells us how to relate these coefficients on each side. And if we put this amplitude through the map, we see that it's exactly equivalent. So the theories are actually exactly equivalent once you're careful to include all the higher order terms because of this lack of transparency in the derivative expansion. And you can check that the higher order amplitudes, the 5-point amplitudes, everything's all the same under this transformation, this map. Okay, so what we have here is a situation where it now conforms with our intuition that the symmetry breaking pattern and the degrees of freedom completely determine the low energy field theory. So that remains true, and this is not a counterexample. But we have this interesting situation where we have an observer who's on this stuck on this three brane. If they cannot tell just from experiments on the brane whether they are probing an extra space, whether their extra dimension is spacelike or timelike, because the symmetry group of the full 5-dimensional space-time is the exact same in both cases. Just from experiments on their brane, they can't tell whether they're in a spacelike or timelike extra dimension scenario. So this actually touches on a typical question that comes up in ADS CFT when we have a conformal field theory that's supposed to be holographically generating an extra dimension. How does the CFT know whether to generate a space-like extra dimension or a time-like extra dimension? Both have the same symmetry group. It's not just symmetries, it's something else that has to be telling you. And in this particular case, there's actually no difference. They're completely equivalent from the point of view of the physics on the brane. Of course, we think that physics in a space-time with 2 time dimensions should be somehow pathological. So we expect that once you make the bulk dynamical in any way, you introduce dynamical gravity into the bulk, you introduce other dynamical fields into the bulk, that something should go wrong and you should actually be able to tell the difference. But as long as the bulk is just a fixed space-time like we have here, then there doesn't seem to be a way to tell. Okay, so in the last few minutes, I'll say very quickly. So this was all just the case of a simplest case of a single scalar field and what kind of space-time uh, shift symmetries you could have and how they're deformed and so on. So of these possible deformations in the time, in the case where you had a flat extra dimension, there are these 2 independent inequivalent deformations. But in the ADS case, there was just one once we have this equivalent. We'd like to know how all of this extends both to branes, which are curved, and to other fields, multi-fields, higher spin fields, and so on. So a starting point of this is to ask about higher spin fields, shift symmetries of higher spin fields. So that was, we classified in this paper here, if I have a higher spin massive field, say on anti-de Sitter space or de Sitter space, it turns out there's a discrete set of masses at which you get a shift symmetry that's parametrized in this by this constant tensor in the ambient space with this complicated tableau.
But
So
are these special values precisely the ones for partially masslessness?
they're related to that. So they're actually the longitudinal modes of the partially massless fields. So if I take
Okay, but this symmetry, does it have well, for instance, if you take s equals 0, if you take critical ADS scalar, then there is symmetry of this sort in ambient space, which is just adding of a certain function of x satisfying well, of this type symmetry.
Yeah.
That's why we say that singleton lives on the boundary of ADS space, because if we quotient these modes, we get a singleton on the boundary. Is it similar idea here, or it's something
Yeah,
else? Just
yeah, it's similar here. It's not the singleton though, because it's different masses, but it's
no,
the
no.
one.
If you take spin 0
Yeah,
case and take critical mass in ADS, which corresponds to singleton,
yeah,
or higher, or these other critical values, would it be this critical, or I confuse something?
yeah. No, it's not this. So this is not
It's
the same.
different.
Yeah, it's different. These are not the same mass values that give you the what you're talking about. So these are things that come from, for example, if I take a massive spin 2 and I take the partially massless limit the longitudinal mode that decouples, that gets a shift symmetry.
Okay, well, probably I have to understand. Okay.
Okay, but yeah,
Okay, thanks. Anyway,
yeah, that's a whole nother talk. But
so it's different values of k. You're saying, right?
Yeah, that's right.
Very strange. Okay.
But
okay.
Yeah, they're exactly they're the longitudinal modes of massive fields that decouple when you take partially massless limits. Here, this might help. So this is what they look like from the point of view of the dual CFT conformal dimensions. So here's the spin, here's the dimension. So the partially massless fields would lie down here. And these are the shift symmetric things that decouple. So they're the integer conformal dimensions.
Yeah. Well, okay. Anyway, let's go. I don't think I can quickly get the difference, but I will have a look.
Okay, yeah, that's a whole another talk, but I'm happy to talk about this because it's an interesting phenomena that happens. But this should provide sort of a generalization of what we just talked about to the higher spins. And in particular, if you look at the algebra of these shift symmetries, there's a whole sequence, an infinite sequence of finite dimensional algebras that are allowed when you include these higher spins. So the simplest example is this for a single scalar. This k here labels what we were calling the power of x in the shift symmetry. So k equals 2 is what we were calling the special Galilean before. There's a non-trivial algebra that it satisfies, but there's this whole infinite sequence of other algebras that was deduced in these papers where you involve other fields, specific sets of higher spin fields. So there should be theories, nonlinear theories of these particular collections of fields that have these shift symmetries that all mix with each other. And as you take limit to infinity, there might be even some infinite dimensional version which has infinite sets of fields that you could think of as some longitudinal mode of a theory like the Vasiliev theory. So this is all interesting stuff that I'd like to look at, but for now I'll summarize. So this example we showed, we have an example where we have an effective field theory on a brane where it can't tell the difference between a spacelike and a timelike extra dimension. And it essentially comes because this power counting, the derivative power counting for the effective field theory is obscured when you use these geometric constructions on the brane. So that's just a general lesson of effective field theory where you're using these geometric constructions, is that the power counting can be obscured. Higher order, what you think are higher order terms can actually contribute to lower order stuff. And it's not transparent in the geometric constructions, but it is transparent in other reparameterizations. So we'd like to generalize to see if there's other higher spin multi-field versions of this. And one final thing I'll mention is this recent paper where they looked at novel ADS representations, so novel representations on ADS that didn't actually correspond to things we think of as ordinary propagating fields on ADS, but things that you could think of as propagating on a two-time de Sitter space. So this is something I don't know much about because I'm still trying to understand, but I thought I would just mention this connection. Okay, so I'm about out of time, so I'll stop here. Thank you.
Thank you very much. Are there any questions?
Can I ask a question? Do you hear me?
Yeah, we can hear you.
Okay. Thank you for your talk. My question is about generality of this construction. Suppose you are a simple guy and you start from 4 dimensions and you just add to Lagrangian any terms you like and then impose a symmetry. On the other hand, another guy is performs a geometric construction. Is there understanding and that you will reproduce all the terms? And related question is about Wess-Zumina terms. How do you get them?
Yeah, so I mean, the expectation is that if you do your brute force construction of just writing all possible terms and demanding the symmetry, and somebody else does a fancy geometric construction, as long as the symmetry group is the same, so as long as the symmetries you're imposing satisfy the same commutators as the geometric construction, then the theory you get should be the same at the end of the day. I mean, it'll be some complicated field redefinition probably, and you may not be able to find it, but it should be the same theory at the end of the day. That's
Is this
the expectation.
A theorem
It's
expectation? Or?
Yeah, it's a folk theorem. So I'm not aware of any proof of this in the case where you have spacetime symmetries. I would like, if anyone knows a proof of this, I'd be very interested. So in the internal symmetry case, there is a proof because it's essentially the coset construction, but for the spacetime symmetries, it's not because of the subtlety with the inverse Higgs constraints. So it's just a folk theorem. I don't know any counterexamples. And then for these Wess-Zumina terms, so they can be classified by a certain Lie algebra cohomology. So there's a relative Lie algebra cohomology, it's called, between the unbroken and the broken symmetry. And you can use this to classify the Wess-Zumina terms. There's this famous paper by Weinberg where he does this for the chiral Lagrangian in QCD.
Okay, thank you.
Yeah.
More questions?
May I have a couple of maybe naive questions?
Yeah.
Okay. So the first one rather technical. So did I understand it correctly that in fact in all these Lagrangians that you considered, the actual dynamical variables was just the embedding function of this brane into the higher dimensional space-time with fixed geometry.
Yeah, that's correct. Yeah.
So basically, this is, as I understand, the codimension of this brane is just one. Yeah.
Right.
So is just one function. Then is it right that in fact this means that all these Lagrangians were rather complicated. They all contain they are written in terms of the extrinsic curvature and the intrinsic Riemann tensor or Ricci tensor, but they are actually not independent because they are all parameterized by just one function and the corresponding derivatives of this function on the brane.
Yeah.
And the question is, still, these Lagrangians that there are many of them, they are all free of ghosts, so they do not have high derivative terms because of this specific Galilean or combinations.
That's right.
Between this. Okay. Then maybe one more question. Well, maybe it is very, very, very general. So, what is an ultimate goal of all these programs, so to say?
Well, I would like there to be.
These models, you see, when these models, in terms of just one, so to say, scalar degree of freedom, how do you expect that these models should be somehow generalized in order to include gravitational transverse traceless degrees of freedom or some other degrees of freedom, so that to make it more physically reasonable from the viewpoint of some maybe cosmological applications or whatever else?
Yeah, very good. Yeah, so what I showed you was just for the scalar. So we pretty much understand the scalar. In other words, we understand what the complete classification of all possible broken symmetries, broken spacetime symmetries looks like. So we would like to generalize this to the other degrees of freedom, other spins, other types of fields, multi-fields. So the ultimate goal would be an understanding of, if you give me any collection of fields, what is the most general pattern of spacetime symmetry breaking that I could possibly have?
but the inclusion of these degrees of freedom, how would you expect to do this? You will embed this brane into some generic geometry, not
Yeah,
just a
well,
symmetric one.
yeah, it may be that way, or it may not even have an easy geometric interpretation. I mean, it would be better if you had some understanding of, just from the group theoretic point of view, of what the broken symmetries are and what algebras they can satisfy. Then you wouldn't be reliant on a geometric construction like this.
Because I expect that if you would generalize the geometry of embedding space to something generic, then you will get ghosts on the brane.
Yeah, that's right.
Because
So
all this high derivative Lagrangian will actually stop being this distinguished set of Galilean Lagrangians without well.
Yeah, that's right. So you may not have these special terms anymore, but you may, we don't know. So there's one case where we do know if we extend to a higher codimension brane. So that's a situation where you have a multi-field, multiple scalar fields. In that case, there are still geometric invariants you can write, which descend from these Lovelock terms, which are free of ghosts. So in that case, there are ghost-free terms you can write. There's just fewer of them, but you can write them.
I see.
Yeah.
Okay, thank you very much.
Yeah.
More questions? If not, then let's speak. Let's thank Kurt for a very interesting talk, and see you next seminar or before. Thank you.
Thank you.